45.
Well, I said, yeah, I open up the, well, I planned on opening the bridge up at 7:45, but just because people like to just sort of chat.
Yeah, kind of normally, unquote, we meet at Griffith Park Observatory, and from 7 to 8, guys are just hanging out, chatting, you know. And so I guess this is the equivalent of that.
Sounds like we're going to have a good guest speaker.
I am here. I'm connected.
Hi.
Hello.
Hi, welcome.
Yeah, old fur face. Jack Eastman out here in Colorado. It looks like this thing's going to work again for me. So here I am.
Good news, Jack.
Hey, everybody.
Hey, Daryl.
Hi, Joe.
Spencer, can I share my screen?
Sure, go ahead.
Are you still a little chess piece?
Wow.
It's current Matt Wilson.
Yeah, I'm about 3 miles from there.
Really?
Yeah, I'm in Pasadena.
Really worrying email today, Daryl.
What's that?
The one about the fire coming up towards Mount Wilson.
Oh, you mean from
I did. Unmuted.
from Hale? From Sam Hale?
No, there's one here. This is 100. This is 60 inch.
Yeah.
So yes,
Yeah.
I was pointing at that
Yeah.
and said, is that?
Hey, Nazar. You know how far away it is, Daryl?
When I look on another map, I'll reshare for a second. Let me show you this. So this is a fire map. I think Tim Thompson sent me a link to this place. So you can see here. Here's the outbuildings. Here's the
Wow.
60 inches here, the 100 inches here. This is an upslope. These are what do you call it? Can't think of the word.
Elevation lines or whatever?
Yeah,
Topographic, yeah.
topographic line. So here's 5,600. We know that Mount Wilson is what, 57 and change. So another 100 feet up from here. So it looks like 1, 2, 3, 4, 5. It's like it's 1,000 feet down the hill. Let me see. I think I can do.
Is that something you got earlier, Daryl, or is that right now?
I think this is pretty current. Looks like it's only 800 feet away now.
Wow.
I can't see the URL for this. What is the URL?
It's Cal, C-A-L, Topo, T-O-P-O, .com.
What?
I'm watching the webcam and I can see the fire is almost at the observatory now. Looking east, you can see a very bright glow on the HP Ren cameras.
Yeah, here it is right here.
Wow.
I'm sharing my screen. This is current. This is the update. I got it live on HP Ren here. So it's really close. And according to this, the measurement from the edge of this, which I'm assuming is the edge of the fire, is now like 1,000 feet. Earlier today, I think I measured it from back here. It was like 1.25 miles. So it's made some.
So have they got firefighting resources in place at the observatory?
There are about 40 firefighters, or there were, and I assume there still are, on the mountain. To the best of my knowledge, all of our staff that was remaining have been evacuated by the firefighters. There's nobody there now except the fire department. They have 2 structure defense strike teams, and there was a hot shot crew there and 12 engines when they were last counted. So we may take a hit. If we do, it'll probably be the cabins that are downhill from the monastery. Those cabins will be very hard to protect. The monastery itself is in pretty good shape. All the fire shutters are closed. It's a stone building. It's nothing around it to burn. And some of the Chara optics might get a lot of smoke on them, but I think the 100-inch is not really seriously threatened.
Just so you don't feel so bad. Oh, you can feel bad for some other people too. There's other fires.
And sure hope he can save the 6-inch refractor.
A lot going on. Okay.
Well,
Yeah, I agree, Jack.
I like to save everything.
Anyway,
I'll drink to that.
Yeah. Heavens to Murgatory. Jack Eastman's actually using a computer. Hard to believe.
Well, thanks to a benevolent neighbor, he loaned me an iPad and wormhole, so I'm able to at least keep contact. Our libraries, of course, have all gone south.
Yeah.
Any fires your way, Jack?
As far as I know, that one that's north of Rocky Mountain National Park is still going pretty strong. The one out near Grand Junction, which is now the biggest one in the state history, everybody's making a big deal about that. I'm not sure what the status of that one are. I'm relatively smoke-free at the moment.
Oh, wow.
See Pikes Peak 50 miles down the road. So
Oh, wow. Yeah.
here for a while, I was lucky to see about 12 miles.
Yeah, we couldn't see across the street yesterday. Right now, we're about 180 on the air quality.
Oh boy!
In Berkeley, California.
Oh, gee.
Yeah.
What are you guys tempered? I understand you guys are cooking pizza out on the sidewalk here.
That's
the last
right.
few
Yeah.
days.
Tires are blowing up. Pizza's cooking. Everything's good. The beer's a little warm.
Well, we were that way, and then about 2.5 a day and a half later, with 1.5 inches of snow.
Yeah, you told us.
I loved it when. Yeah, the temperature went from 38 Celsius to 38 Fahrenheit in something like 30 hours.
What's a letter? Yeah. Ouch. Is that 6-inch still in mothballs?
No, it's been restored.
It's working.
I was up and
Yeah.
running. Very good.
It works great. It's got the original mechanical governor on the
right. Yeah.
on the RA drive. You can watch the little thing spin around.
Right.
It's great.
Yeah, I used it in the 50s and 60s. It was
Yeah,
spinning.
same here. The one at UCLA, they replaced the weight-driven clock with an electric drive, and every time I went to use that telescope, there was a note on it: "Do not turn on drive," and the little glass case looked like it had been smoked. Seemed like they had fires in that thing one after the other.
Good.
Put the weight-driven clock back, you toads.
Yes. Yeah.
That's what we use.
If it ain't broke, don't fix it.
Yeah. God, yes.
Hi, everyone.
Yo.
Tim?
Yeah.
Hi, Rob.
Hey, how are you?
Doing good. Good to hear from you. I haven't talked to you in a long time.
Yeah, likewise. I'm doing okay. Anyway, I'm just going through some stretching exercises. For those of you who are on my Facebook friends, I had hurt my left shoulder a while back, and right now I'm on the mend. So hopefully they're saying another 2 to 3 months of stretching exercises. The diagnosis was a rotator cuff strain. So anyway,
Probably caused by holding Alan at arm's length.
Yeah, something like that. Whatever. But I was wondering if anybody had heard whether the Lockwood Valley site was going to be open on Saturday.
Well, I expect it can be. You know, it's open for star members, but you know, who knows? It was so smoky last Saturday on the work party that we didn't bother. We didn't stick around. We didn't even discuss it. One person, Alicia, had said he was going to be staying, and he did bring equipment, but I doubt that he was going to get any imaging done.
Yeah. All right, because the latest news I heard is that Los Padres National Forest was closed, but that situation could be changed.
No, yes, it was closed on when I drove up there on Saturday.
I see.
But that doesn't affect getting into Lockwood.
Oh, okay.
Not unless the fire is like going right across the highway.
Yeah. Wow.
Because that's in private property and everything.
Oh,
so
okay.
who
I understand.
knows? Who knows?
We'll see.
Kevin,
because I do plan on coming up. So
Kevin, this is John O'Brien. Al sent me a text just about an hour ago of a bright red sunset.
Yeah.
So I think it's still pretty smoky up there today.
Okay. Yeah. No doubt.
Okay.
Mount Pinos is closed.
Yeah.
Yeah, that's in the middle of the forest.
Yeah.
National Forest.
Okay, well, that's all I got for now.
One minute to lunch.
Yep. Had a pretty good turnout this time.
How many?
35 so far.
Oh,
that's great. Hey, Nasir.
Quick comment here. Dave Nakamoto read his article on Biela's Comet in Sky and Tell, first class.
Yeah, I read that too. It was really cool to have Dave in the club and know him personally and see such a great article.
Yeah. One thing I would ask is talked about the meteor rate per hour during those showers. Kind of wondering how that compared to the great Leonid meteor blizzard of 1833.
Me. But I saw the Leonids, what was it, 98 or whenever it was, when it was really impressive. And from Lockwood Valley, I could watch the meteor trains for like 10 minutes in the binoculars as they swirled around in the stratosphere. It was really impressive. Ever since then, I've just been bored by meteor showers, you know.
Okay, guys, I think we will get started if I'm not muted. I'm not muted. Okay, we will start tonight's general meeting for September. 2020. Just want to welcome everybody on that has come to the meeting on Zoom. In fact, we will be using Zoom for general meetings until Griffith Observatory is open again. And the powers that be, I think Tim has mentioned, probably will not be until next year. So we probably will be doing this till the end of the year. Okay, some very important announcements. I'll start off with a very important announcement right now. We got a call from Mary Brown today that Sue Sovereign, that is Dave Sovereign's wife, has passed away. So we want to send our condolences to Dave Sovereign and his family. So just wanted to mention that. That's we got the news today from Mary Brown, updated us on the news. Now we could probably go ahead and have Andy send that out on the website, so everybody that knew Dave Sovereign and knew Susan Sovereign, or Sue Sovereign, at least most of us probably remember Sue from the banquet. So we'll go ahead and send out an announcement, have Andy send out an announcement on that, okay? Another item that we would like to go over, for starters, is last month we discussed, and the board members have been discussing for the last couple of months, a life nomination for a life membership nomination for LAAS for Lou and Carla Chilton. We sent it out at the last general meeting. We need to get a confirmation of a majority of the membership participants tonight. So Spencer, you must have set that up to be able to count the approvals. Did you do that, Spencer?
Yes, I did. Actually, probably the simplest way of doing it, if you click on the participants icon, and you can do a yes or no. So if everybody could click on participants icon, you get a little screen that pops up and it says yes or no on it. So I got 12 yeses already, 14, 15, 16, 17, 20, 21 yeses. They got 22 yeses. So that's the majority.
You've already got a majority.
You already got a majority.
I was going to say, Jack here, I don't know if that worked for me or not, but I will tell you yes over the air.
Okay, 23.
Yeah, and Spencer, Rob Komodo, I don't know if this works either, but I'll say yes.
Okay.
Absolutely.
All right. Okay, so I think we have overwhelming majority that have voted yes. So I'll deliver the news to Lou and Carla.
So it looks like it's official that Lou and Carla Chilton are life members for LA Astronomical Society. We will notify them as a results of the meeting tonight. Okay. The next information that we need to go over. So far, we've had Garvey Ranch, Mount Wilson, and Griffith Observatory have been closed for quite some time. We're not able to use the facilities, and we suspect that they will be closed until next year at the earliest. And we also got a late breaking news from Mount Wilson. I'm going to have Tim Thompson update you on the Bobcat fire that was approaching Mount Wilson. Tim, it's yours. You got the floor.
Well, the Bobcat fire is still approaching Mount Wilson, and judging from the webcams, HP RenCams I'm looking at right now, the east-facing camera, it's almost there. It was supposed to approach by Echo Rock, and that looks like what it's doing. Earlier today, to the best of my knowledge, the 4 remaining staff members, 2 for MWO and 2 for Chara, were evacuated. Right now, well, last I heard, and it should still be valid, there were 40 firefighters on the scene, 12 engines. there were 2 structure protection strike teams, and there was a hot shot team up there as well. And they can use the main parking lot for flying in equipment if they need it. Our fire suppression system is fully charged, so we have about 640,000 gallons of water on site, in addition to whatever the water tenders bring. I don't think the helicopters were able to fly today because of smoke. It was pretty intense, and they have to fly down low, and they can't do that in the intense smoke, or they fly into the mountainside. And so there wasn't much in the way of fire retardant drop today, so far as I know. So right at the moment, the fire is perilously close to the observatory, and during the course of this meeting may very well enter it. I'll be watching that while I'm listening to Luisa with my other ear. And I'll mute myself before I scream if anything bad happens.
I have a current vision one up. Can I share my screen? Is anyone else sharing? No?
Yeah, please do.
Oh, good grief.
Everyone see that okay?
Yes.
Yeah, I can see it, but geez.
It's really scary. I sure
Oh,
you can
man.
see the city through the
Oh,
flames.
man.
Mike.
Yeah.
So that was a refresh right there.
Mm-hmm.
It's really, really close.
That is
Yeah.
close.
I'm sorry to see.
But there's a lot of firefighters on the scene, and they should be able to protect most of the big structures anyway. If we take a hit, it'll probably be the cabins that are down below the monastery, which are basically in the forest and really hard to defend. I don't see anybody trying to defend those, but the monastery's in good shape and is not really very burnable anyway. It burned down twice in the early 1900s, and they got the message. And so the current monastery does not have a lot of outside wood, and it has fire shutters, steel fire shutters that have all been put in place. So I'm not worried about that. And the 100-inch is in good shape. Chara might have some problems with the outer telescopes.
Well, you have to also also remember one of the reasons why they can't put a lot of fire helicopters and aircraft in the area is because of all the antennas right next to the right next to it. There's a massive amount of TV antennas and radio antennas right next to the observatory, as everybody knows. So that's probably a hindrance, but it sounds like at least they got a game plan right now.
Okay, well,
They do. We've got people there ready to go to work, so we'll see what happens.
Okay, well, thank you for the update, Tim, and thank you for the update, Daryl, on the link for the webcams at Mount Wilson. Okay, thank you. Okay, the other thing we're going to be doing is we will be doing the next meetings, the next general meetings will be the general meetings and the board meetings are all being done by Zoom now. So the general members can go on to the board meeting and participate in the board meeting when we have the board meetings. And we will be probably doing Zoom at least until the end of the year, till next year, when everything else opens up. Okay, thank you for the update, Tim. And now we'll go on to the next item coming up in November. We normally have the November meeting. We normally have the November meeting reserved for nominations of officers and board members. So we're going to have to do that via the internet link this time. So I think Spencer has set that up to where we will be able to do the nominations for officers and the board members, so we can get the elections taken care of. I kind of don't think Tim was mentioning we probably will not have a banquet in January, right, Tim?
Well, I have not reserved anything for the banquet, and I don't think we're going to be able to. So,
well, we just
so
have
far
to wait. it looks like that's a wait and see right now on that.
Yeah.
Okay, and of course, all, like I mentioned, the board meetings and the general meetings are all being conducted via Zoom, and we can get, and contact Spencer for the information to get the Zoom link. So any members that want to go on to the board meeting or the general meeting can look at the meetings via Zoom. Okay, the other thing that we have noticed, the amazing thing about it, is even during this total lockdown of everything we've got, it seems to be our membership is going up in LAAS, and we want to thank all of the new members and all of the memberships for LAAS. The last board meeting, we were amazed to find out how many new members we had at the last board meeting. So thank you all for joining the club, and hopefully next year we'll be able to start doing some stuff except sitting here staring at our computer screens all day. Okay.
Do we have any new members logged in, Curtis?
That I don't know. Spencer will have to answer that question. In fact, how many, do we have any new members logged in?
Yes, we do.
Okay, they're okay.
My name's Mike Gardner, and I am a returning member from the 1960s and 70s.
Okay, welcome.
Welcome
Thank
back.
you very much.
Welcome back.
Okay, next one.
Wow.
My name's Ryan. I'm a new member. I was born in the 70s.
Oh.
Welcome, Ryan.
Thank
Yeah,
you.
welcome.
Welcome. Welcome.
Yeah.
Okay, any others? Well, it looks like we got two of them on the Zoom tonight, which is pretty good, but we do have a very good amount of our members renewing, and we do have a lot of new members also, which is very encouraging, considering we're all, like I said, we're all sitting here in front of our computer screens, looking at our computers all day long. Okay, the other thing I wanted to mention as an announcement, we have a new website for LAAS, for LA Astronomical Society. We have a new website, and Daryl, have you sent that? Has Andy sent that out so members can click on it and take a look at it, see what it looks like, and make comments? Has that been taken care of, Daryl?
No, the official launch of the website is going to be at the next general meeting. It is ready, but we still have a little bit to do. We haven't actually moved the name over to the new website, so we'll have to do that before we really send anyone the link.
But Daryl, I think
at the next board meeting, we're not going to have a speaker. I'm going to be presenting the website, and we'll do a show and tell of the website, and then probably take questions and comments and ignore all of them.
if any member wanted to join the committee that's working on the website and help participate in the next few weeks to give us some feedback, I'm pretty sure we could open up the test site for that. So just get a hold of one of the board members, Daryl and Alicia and Greg, and we'll see about, because several members have already contributed some comments that have been really helpful.
Anyone, if you want to contact me, I will send you the current link to the site, but I just don't want people to get confused, because if I send you the site, then suddenly, next month you try and go there and it's not there because you're going to the wrong place. So if you know what you're doing, send me an email at the Mount Wilson coordinator at LAAS, and I'll send you the link, and then you can give us some feedback before it actually goes live.
Yeah, they can be our beta testers.
Come on, beta testers.
Okay, well, thank you for updating us on that, Daryl, because I wasn't sure whether or not that went out or not, or what the plan exactly was on that website. But I know some people that have looked at it have said it was very, very well done website. So it's a very good job you guys are doing. Okay, thank you, Daryl.
All right.
Okay, the next thing I want to discuss is, if you register for anything on the LA Astronomical Society, you buy anything on our merchandise part of the website, do remember that you can go onto Amazon Smile and you can make a donation to LAAS, as it looks like it's 0.5% of your purchase, whatever you buy on Amazon. So if you go through Amazon Smiles, then you'll at least get to make a donation to LAAS. So I wanted to mention that also. Okay, and then the next item on the agenda is our next general meeting will be on October 12th, Monday night, October 12th, and that will also be via Zoom. Okay, so I think I've got through all of the general announcements. Does anybody else have any other announcements that I may have missed? Not hearing anybody, I guess we can go on to our speaker. Our speaker tonight is Dr. Luisa Rebull, and her talk is called Getting Your Hands on Real Astronomy Data. I'm going to go ahead and turn this over to Spencer, and he can take care of the rest of taking care of the speaker for tonight. Okay, Spencer, it's yours.
Well, actually, I'll leave it to Luisa since she's got the she's sharing the screen now.
Okay,
And,
great.
Right.
Okay, great.
Dr. Rebull, you want to introduce yourself?
Sure. My name is Luisa Rebull. I work at Caltech IPAC, and IPAC is the infrared, well, it used to be the Infrared Processing and Analysis Center. Now it's just a word, IPAC. And I work specifically for URSA, the Infrared Science Archive. I study star formation, but what we're going to be talking about today is how to get your hands on real data. Since so many of your regular facilities are closed, I know it's not so fun to spend all your time in front of the computer, but this way at least you'll have data to play with. So there's something to be said for that. I'm going to try to keep an eye on the chat window as we go along here. So if you have questions, just drop it into the chat and I'll get to them as soon as I can. Okay, so this is roughly what I'm going to cover. So we'll do a little bit of citizen science, and then I'm going to start giving you a crash course in what you need to know to get into real astronomical data. And I'm confident that some of you will know all of this, but some of it might be new for many of you. So hopefully there'll be a little something for everybody here. We're going to talk about colors and artifacts and spatial resolution and all sorts of good stuff. And then I'll show you how to get into some of the archives at URSA. And if we have time, we can do a live demo. The important things have a box around them like that. And I will put up a web page at the end that collects all of the links that I'll mention. So for astronomy citizen science, there are so many programs out there. In fact, that's some of the original citizen science programs were astronomy ones. And most of these citizen science programs are entirely web-based, so they don't require any special software. All you need is a web browser, whether that's on your phone or on your laptop or on your desktop. You just need the web, and it doesn't require any deep astronomical knowledge. For those of you who are educators, some of these citizen science programs have lesson plans or labs, basically exercises you can do to explore what the science is for the stuff that they're talking about. Some of them have hooks. The really good ones have hooks to go further. So for example, you may be looking at how a star varies with time, and then buried deep in there, there is the actual right ascension and declination of the star. So when you're ready to go further, many of them will have hooks for you to do that. So Zooniverse is one of the oldest and the original astronomy citizen science programs. And so if you just go to Zooniverse, there's a ton of projects that you can scroll through the list. SETI at Home is another venerable citizen science project looking for extraterrestrial signatures in radio data. There's the International Observe the Moon Night, which is specifically moon observations. There's the Globe at Night, which is specifically quantifying light pollution. There's the Great Worldwide Star Count, which is another light pollution one. There's something called Stardust at Home, which I don't think is operating anymore. But for that, you were looking for dust particles in aerogel. Then there's Citizen Sky, which is part of the AAVSO, and it studies variable stars. And then CosmoQuest has a whole bunch having to do with crater mapping on many different bodies in the solar system. And I'm sure I'm missing some astronomy projects in this list. So if you go to Zooniverse, this is the kind of menu that you have. I'm not really expecting anyone to read all those tiny little fonts, but you can go to the web and pick what you're most interested in. And most of them will give you some kind of training, right? You do a short tutorial to wrap your mind around what it is that they're asking you to do and what you're trying to help them find. And then, give you a tutorial of exactly what they want you to do. And usually they're not asking for hard things. Kids can participate to exactly the same degree as adults. I know plenty of kid grandparent teams that do these kinds of things. So, and the important thing is you do not have to be perfect. The whole way citizen science works is that they have at least, I think, 20 people look at each thing that they want you to look at. And so even if you get it wrong, the mistakes will average out over time. So, but why then are they asking for your help? Because the human eye is really good at finding patterns, and it's often very much better than computer algorithms. And so that's why they do this, because you're helping them do real science. And so there's plenty of papers that have come out where several of the people in the author list are people who helped with the citizen science, who found the thing in the citizen science data set and who helped contribute to whatever it is that they found or discovered or analyzed. And so you can see some of the author lists are very long because they're including all the citizen science participants who helped with that object. So if that's the only thing that you remember for this talk, and especially if you really get into any of these projects, then, you know, I've done my job for the evening. But perhaps the things I was just telling you maybe just whets your appetite and you just want more. So we're going to go down the digital rabbit hole and see what else we can find. So it really is true that there are more data than the professional astronomers can handle. There's more coming in all the time. To be sure, that means the professional astronomers are doing the things, you know, if they start a survey specifically to look for, say, brown dwarfs, they're going to be looking for brown dwarfs. But that doesn't mean there aren't galaxies in there. So there's lots of good stuff in there. And there's plenty of science in the archives waiting to be found. And any facility that comes from US federal dollars, from public funding, is supposed to have a publicly accessible archive, because these are your data too. NASA is really, really good about this. The NSF is getting there. Europe is catching up. Other countries, not so much, but they're getting there. NASA data alone, though, will keep you busy for quite a long time. So the NASA data that I know of, there's astronomical data, of course, which is what I'm going to be spending most of the time, the rest of my time here. But there's also plenty of moon and planetary data and plenty of Earth observing data. Now, the moon and planetary data is a different format than the astronomical data, and the Earth observing format is yet another format. But still, there's a lot out there, and there's a lot of ways for you to get access to these archives. But because, you know, these archives are at the end of the day designed for the professional astronomy community, that's their primary audience. That's what they're funded to support. However, professional astronomers span the spectrum from an emeritus professor barely able to read his email to a young woman starting her very first research project in the summer. So because we have to make all the data accessible to all of those people, it's also available for you, and you should be able to get into it without too much trouble. But you do need to become, you know, familiar with some of these conventions and some of the jargon and even the file formats, because it's not going to arrive on your desktop with a little bow on top. It's going to be a little more complicated than that. So the very first concept I want to get across is that just don't use Internet Explorer. Seriously, don't do it, or for that matter, Microsoft Edge. And you should go get Firefox or Chrome. And because MSIE and Edge are buggy and have security holes, and because most astronomers use Mac or Linux machines, there's not a lot of users who use those browsers. And so since the archives are operating on a shoestring, we're not going to invest a whole bunch of money to support browsers that our primary audience doesn't use. So, you know, that's just the reality of it. So you need to go get Firefox or Chrome. Because, you know, the archives might not even work with MSIE. In fact, several years ago, we discovered that for 6 months or so, our main homepage at URSA wasn't loading at all on Internet Explorer, and nobody had noticed in 6 months. That's, you know, that's the reality. Okay, the next big concept is the mechanics of how the images work. So all digital images are ones and zeros. That's how it gets stored on your disk. It's just that your computer knows how to handle it. So images from your digital camera, which are typically JPEGs or GIFs, are typically 8 bits deep. What do I mean by that? It means that each pixel has 2 to the 8th or 256 discrete levels of information for each pixel. So that's only 206 possible values in each pixel. That usually doesn't matter to you. Like if you have a picture of your friend on your phone, you don't notice that. But if you're a graphic designer or a web developer or an astronomer, it does matter. because astronomical images have a much greater dynamic range. They are at least 16 or even 32 bits deep. So that means 2 to the 16 or 2 to the 32 different possible levels in each pixel. And when you convert that back to a JPEG, you're compressing 65,000 levels into 256. And so you lose information. And as a result, then you're losing the photons that you worked so hard to catch. So another way to think of bit depth is like little containers of water. So the first thing I was trying to find is, okay, well, it's a tiny container for water. Well, let's get an array of thimbles. You can't get very much more than a dribble of water in each one. So maybe 256 drops, say. Each one of these little vessels overflows quickly. And that's okay for images taken with your cell phone. And so then I was like, okay, well, what's bigger than a thimble? Okay, teacups works. Now I can get more than a dribble of water in each one, but they still overflow really easily. So I'm digging around on the web trying to find what's bigger than teacups. Trash cans. All right, an array of trash cans, because now we can fit 65,000 or 4.3 billion drops of water in each one of these trash cans. So that's sort of the gut, your gut response, right? I'm getting some noise in the background from somebody. If you've got the TV on or something, maybe mute it. Thank you. Okay, so the main concept is for images from your digital camera are usually 8 bits deep, which means there's 256 possible levels in each bucket. But astronomical images can handle more than that. And it turns out in your camera, you actually have 3 arrays, but we'll get to that in a second. So the analogy of thimbles or teacups or trash cans is not perfect, but it does okay. And usually if you're going to buy like a real camera, not just one that's part of your cell phone, usually they try to attract you with the total number of pixels. But that's talking about how tightly the buckets are packed together and how many total there are. The depth of them is what we're talking about with bit depth. And if all of that's still really confusing, just think of it this way. Astronomical images can hold a lot more information than JPEGs or GIFs. And moreover, JPEGs are lossy compressed. They actually, when they compress the data, they actually lose information. And I don't know if you can see it on your screen, but so you may have to do experiments on your own. You can save a file as high quality JPEG or low quality JPEG. And I don't know if you can see, but especially where the, like in the cat's ear, where there's a big difference between dark and light, you can see ringing, you can see fuzziness around the edges of the cat's ears. And it's clear that you've lost information. So especially in astronomy, somebody worked really hard to collect all those photons. So don't lose them as the very last step. If you're doing less compression, that's fine. It's lossy compression that you don't want to do. So in other words, if you want to do real astronomy images, you cannot be using JPEGs or GIFs or even PNGs. So what do you use? You use FITS files. FITS is Flexible Image Transport System. Most professional astronomers use this format. It's not compressed. There's no lossy compression, so there's no loss of information. Usually there's a plain text header and then the binary image. And the header it can be really big or it can be really small. It can be just information about, this is where I was pointed, right? It could also be, this is where I was pointed from this observatory at this time with this wavelength. And here's the data rejections steps I've done to this image before you're looking at it. So it can be long or it can be short. And the binary image itself can be a single image or it can be like a stack of images. And it turns out also it can be a table of data. You do need to have then software that can read FITS. So there's software called ImageJ or MaxMDL, both of which that can read FITS files. Photoshop, which is not free, does have a free plugin called FITS Liberator. But at the end of the day, astronomers really like free software. So I'm going to show you the Ursa tools, which are all free. There's another really popular tool called DS9. If you just Google it, you'll probably find the Star Trek show. You need to Google DS9 and Harvard to find DS9, the software package I'm talking about. It's not completely divorced from the DS9, the TV show, but that's a different talk. And then there's a lot of Python tools. So if you speak Python, there's a lot of Python tools that can handle FITS images. Okay, color in images. So we have our array of buckets or trash cans that have collected all this water. How are we going to display all of these water levels? How are we going to represent the numbers on our screen? So we're going to take a brief historical detour. This is the very first image from Mars. It came via the satellite Mariner 4 in July 1965. And if you look at it closely, it looks a little strange. And in fact, if you look up close, it's hand colored. That's because in 1965, computers were not very fast. And so the data had come back from Mars, but it was going to take hours and hours and hours and hours for the computer to render it in an image. And the engineers and scientists didn't want to wait that long. So they literally printed it out and colored it in. And if you don't believe me, there's pictures. Truly, they literally printed it out and colored it in. And the way that they did that was the numbers that were in the image corresponded to a particular color. So it's like color by numbers. They have picked, when they did this, a brown-red color scheme, but they didn't necessarily know that eventually the pictures from the Martian surface was going to be red. They were looking for colors that ultimately represented the grayscale that they knew they were going to get out of the computer eventually. And then they sent somebody to the art store and they couldn't find a set of pastels that had 6 or 7 different colors of gray. And so they settled for something that was going to give them these colors between brown, red, and yellow. They could have picked green or purple, but they picked this particular color scheme and they colored it in. And so the hand-done Mars image is on the left, and then the actual Mariner data that came back eventually and was eventually turned into an image was on the right. So it wasn't crazy what they did. I mean, you can definitely see texture in both images that are the same. Obviously, there's the edge of Mars, and you can even see the clouds over Mars in both images. So it's literally color by number. So within each image, we can assign a number to a color. So if you have numbers, say, between 0 and 8, you can assign them to those colors, that rainbow colors that I've drawn out there. But what if we have values more than 8? Okay, well, let's spin it up a little bit. Numbers 1 and 2, or rather 0 and 1 can be black, 2 to 3 can be purple, and so on. Now, at least we can show data ranges between 0 and 17. But then what do we do with 7.9? 7.9 is legitimately closer to green than blue on this color scale that I've laid out. So maybe rather than discrete colors, you need continuous colors in order to represent the data. But we've talked about bit depth, and we know that we could have numbers much greater than 17. So now maybe you can put them in bins like this. So now you can display a much larger range of numbers than you could before. But the key concept is that you are still working with just one image. Values from that one image are displayed as a color, just like a color by number kit you did as a kid. And color table is the term that describes the range of colors that you're mapping the data to. So the ones that I showed you already were, come back here, are the discrete one and the continuous one, but there's also ones with more discrete colors and shades between, through blues and shades through oranges, lots of different things you can pick from. And then the color stretch is how you translate that range of data values that you have into the range of colors. So the versions that I showed you are those lines there, where it's just between 0 and 7, or between 0 and 17, or between 1 and a billion. So there's lots of different stretches you could use. There's many different choices. So you can represent one image as shades of gray, or like in the first Mars image, red pastels. But astronomical images that are taken in just one filter are often shown in grayscale or reverse grayscale, because it's the least distracting way to see the details in the image. And ultimately, it also uses less printer ink. So there's the same image with the same stretch. One is a grayscale and the other is reverse grayscale. And your eye is almost immediately drawn to different things in this image. It's the same data, but you're seeing different details in the image depending on the color table that you pick. So you're not changing the data, you're just changing how it's shown. And if you're someone who's interested specifically in the spiral arms, you might pick a different color stretch than someone who's interested specifically in the core of this galaxy, for example. Okay, so color images. I may be blowing your mind by saying there's no such thing as a color image. And this is very counterintuitive, because after all, you're looking at a color image on your screen right now. But it turns out that that's really what's going on. So we take one image, and instead of scaling it from black to white, we're going to scale it from black to red. We're going to take another image, black to green, and a third image, black to blue. And we're going to stack them up. That is how your computer is doing it right now. This is how your TV works. This is how a projector works. You've got arrays of red pixels, arrays of green pixels, and arrays of blue pixels all intermingled. And when you have something that's faint in all, you get a black pixel, and if you or black region, and if it's bright in all, you get a white region. So all color images are made up of 3 or sometimes 4 separate images. Color photographs have 3 different emulsions, a red, green, and blue emulsion that's stacked up in the film. Digital cameras usually have 3 sets of pixels, red, green, and blue. Sometimes they have 4, which are called C, M, Y, and K. They're always lowercase, and they stand for cyan, magenta, yellow, and key, which is black. So, you know, basically we're talking about how there's, you know, we're creating a color image by collections of single band colors. Now, astronomical images have filters. But here's a demonstration of 3 color images from 1902 when color printing was new. That's how they're doing it. There's a red, there's a green, or rather a red, a yellow, and a blue that's stacked up to make the color image. And there's, this is actually a promotional graphic from some camera company on the web where they're trying to demonstrate their interlacing of red, green, and blue pixels in their product. So in astronomy, I keep talking about taking an image in one filter. What do I mean by that? You can kind of think of filters like pieces of colored cellophane, you know, like sort of old style 3D glasses. Here I've got theater gels because this is LA. And the idea is that they only let in light over a narrow range in wavelengths. You can only let the blue light in, or only the green, or only the red. And it's not a coincidence that the 3 gels that I have here are red, green, and blue. And we were just talking about making color images from red, green, and blue. So the whole idea of the filter is that it makes the light that's coming through your telescope go through a filter before it hits your detector. So you're only recording the light that actually makes it through the filter. So you take an image in one filter, you assign a color, red, green, or blue, to that image from that filter, and then you do it again. And then you do it again. And so you have the 3 colors if you're doing RGB, or 4 colors if you're doing CMYK. You can do it as conventionally, the shortest wavelength is blue and the longest wavelength is red, but you can do whatever you want depending on what details you want to bring out in the image. And in terms of assigning shades of color, again, you can do it any way you want. How you map those numbers to colors depends on what details you're looking for. So lots of astronomy public images describe things as true color or false color. And this is actually a really, really deep question. There's a lot of confusion actually about what is true color. Anybody who has ever redecorated a room in their house with somebody else helping, you know you do not see the same colors the same way. I myself have had conversations in my house about that's pink. No, it's not. Okay, not everyone sees color the same way. And back in 2015, there were two images of the Earth taken from near the moon that just happened to be released on the same day. Both of them claimed to be true color, and they were totally different, which was a really dramatic demonstration of what is true color. And so there's that post from Emily Lakdawala where she talks about all of this with the 2 photos of Earth. And also in this era, this politically charged era, language matters. And the term false color makes it seem like we're hiding something, but we're not. I do a lot of my astronomy in the infrared, and my eyes can't see infrared. So a true color infrared image is meaningless because it would just be black. I wouldn't be able to see anything. So representative color is a better choice than false color for terminology. So there's a common misconception that astronomical images are obtained first and then broken into colors later. That's not how that works. You have to, in order to make a color image, you do need 3 images taken in 3 different filters. You can't separate the photons after you record them unless you've got some serious high-end equipment. I know they're developing something like that at Palomar, but that's the exception rather than the rule. All right, astronomical data. So I've mentioned already infrared. There's a lot of light we can't see. Specifically in astronomy, we're studying things we can never ever visit or even see from another angle. So we absolutely have to take advantage of all the light we get, even the light that doesn't make it through the atmosphere. So there's lots of telescopes and data and archives from telescopes covering the gamma rays through the radio. It's all out there. It's all free. It's all easily accessible. This is IPAC's unique view of the electromagnetic spectrum. We are a tiny bit biased at IPAC because we do a lot of infrared. So I'm going to focus a lot of what the rest I'm going to talk about the infrared because that's what I do. Not every telescope looks at everything in the sky. There are some telescopes that do surveys, in which case they do look at everything in the sky or everything that they can see. If it's a ground-based telescope, they may look at everything that they can see. But many are not. Many are pointed observatories. So that means that they're going to have a list of targets that they're going to look at for a prescribed amount of time. And then the archive will consist of the individual pointings. So in any given archive, your favorite object may not have been observed. That might just mean yet, or it might mean at ever, right? Because if you care about a southern hemisphere object and you're looking at data taken from Palomar, it's never going to see things that are far south. But there are other things that you would be able to find. You need to find in the archives for a southern hemisphere telescope if you're interested in ground-based observations of a southern hemisphere object. Different telescopes are going to use many different wavelengths of light. So a radio telescope is only going to observe in radio. It's not going to collect data at any other broad bandpass. And different telescopes are going to have vastly different pixel sizes. So a single pinpoint of light is going to look truly like a pinpoint to one telescope. It may look like a blob in another, which can be very confusing when you're starting out. And what's also really interesting is that sometimes that's real astrophysics. Sometimes a point source at one wavelength is legitimately a blob at another wavelength because astrophysics. So this is the most famous Hubble image. It's the one that's downloaded the most frequently. It's the Talons of the Eagle Nebula, M16. It's called, this particular image is called the Pillars of Creation because it's showing star formation in the Eagle Nebula. And this was taken with HST with PIC2. There are 3 images in here. So you can see there's the RGB image code that's here. So blue is forbidden line of oxygen, green is H alpha, and red is a forbidden line of sulfur. So they've constructed a 3-color image using these 3 narrowband filters. This image is really rather small. It's only a 1.2 arc minutes on a side. So this is the Spitzer data of the same region. So you can see the footprint on the talons of that HST image, but the Spitzer image covers a much larger area, and it gives you a much better sense of the large scale texture, the large scale, what's going on in a star forming region. And note that this is a 4-band color image. This is a CMYK image where the 4 bands are 4.5 microns, 8 microns, 24 microns, and 70 microns. Now, Spitzer is just recently been decommissioned. Back in the 80s, there was a spacecraft called IRAS, which did the very first all-sky infrared survey. That's the IRAS image. I swear to you, they're lined up. The things that are bright in both. The things that are dark in both. But obviously, the pixels are enormous with IRAS because it was the very first all-sky survey. It was the very first instrument flown like this. So the pixels are enormous. And this is something you have to take into account. You may be more interested in the Spitzer data than the IRAS data, depending on what you're interested in studying. So, you know, the Spitzer data is also cool because here we've got the longest wavelength is 70 microns. That's red in this. But this is from Herschel. Herschel's another infrared telescope. This image is another 3-color image, 70, 160, and 250 microns. So 70 microns is red here, but blue there, because of the range of colors, the range of data that they have, because they're trying to be consistent and assign the blue plane, the blue color plane, to be the shortest wavelength image. And 70 microns is the longest one here. 70 microns is the shortest one here. So you can also see that the Herschel data is much more, shows you much more about the fluffy stuff, the interstellar medium, the clouds of gas and dust that are in the star forming region. Whereas Spitzer has lots and lots of stars, foreground, background in the star forming region, lots of stars are seen there, and not so many point sources, not so many stars are seen in Herschel. So both Spitzer and Herschel were pointed observatories. They looked at specific regions of the sky as opposed to an all sky survey. WISE is an all-sky survey. So this is also lined up. You can see WISE is blurrier because WISE is a smaller telescope, but there's no end to the WISE data. You just keeps going out and out and out and out. It covers the whole sky. So if you were somebody who's interested not just in the talons of the Eagle Nebula, but how the whole star formation works and how it fits into star formation nearby, then you're interested in the WISE data because it gives you the broad picture. Okay. Last big concept that I have here is artifacts. So you're working with real data here. This has not been prettied up for public consumption. So there will be artifacts, by which I mean stuff that isn't really part of the sky in the image. It's just how the telescope responds to light. And you may have a plane or satellites flying through the image, or a bit of dust. You are familiar with this on an intuitive level because here I have an image of a high school football game. And you know intuitively that those lights are not truly gigantic fuzzy blobs with giant purple wings coming off of them and streaks coming down to the ground. You know that. Those are the artifacts. That is just how the camera is responding to these very bright lights. And astronomical telescopes work the same way. So you have to become familiar with what artifacts you might expect. For example, a space-based telescope isn't going to have planes flying through, for example. And also many big images are actually lots of smaller ones knit together. So you might be able to see these tile boundaries depending on the mosaic or depending on the data that you have. So just as a reminder, several years ago, Neil deGrasse Tyson was on the Colbert Show, and Colbert is a big fan of astronomy, and they were discussing this the star that had lots of interesting time variability, and there was a lot of media coverage about what it could be, and so Colbert had Tyson on so that he could talk about it, and Tyson almost cut him off with, "Excuse me, just because you don't understand what you're looking at doesn't mean it's aliens." Which is really an important thing to keep in mind. If you find something that looks weird, you should not assume it's really in the sky. It's much more likely to be some kind of effect in the camera, saturation, scattered light, a plane, even spatial resolution issues, or just a result of how the telescope responds to bright light. So you're going to need to read the documentation and understand what artifacts you're likely to see. And you know, if it helps, get a friend to help you figure it out. Don't call me or email me telling me you've found evidence of alien life, because I promise you there are no giant space praying mantises. I promise you that there are no giant space praying mantises. This is just an artifact. There's obviously a bug on this ground-based image, right? So now, real archives. So I work at URSA, which is at Caltech, and we archive data for NASA at infrared and longer wavelengths. The Exoplanet Archive is also at Caltech. It's also a NASA archive, and obviously they archive exoplanets. NED is the NASA Extragalactic Database, also at Caltech, and they obviously work with galaxies. MAST is based at Space Telescope in Baltimore, in Maryland, and they do NASA optical data. HEOSARC is at NASA Goddard, and they store high energy data. ADS is the Astronomical Data System. That's at Harvard. And they keep track of all astronomical literature. I mean, from the 1800s through this morning, you can go find the data. So you want to learn more about the Venus result from today, you can get access to the paper through ADS. And there's lots of other US archives too that are not NASA affiliated, and there's ones in Europe and Canada as well. But you know, obviously I work for URSA, so we're going to focus on URSA. So URSA is the Infrared Science Archive. It is physically at Caltech. We now have many petabytes of data. So a petabyte is 1,000 terabytes, which is a billion or a million gigabytes. So lots of data, lots and lots of data. We've got all sky surveys as well as pointed observatories, and we have gigantic data sets and small data sets. And many of our largest, most popular data sets are all in the same sort of interface. So once you master that, you can figure out all the others. I'm going to point you first towards a tool that we have called Finder Chart, because it is sort of a good place to start. It gives you the same chunk of sky in several different wavelengths from several different surveys all at once. And it looks like this. So when you load it, there's a place to put in a position. You can put in a name, or you can put in a coordinate. You can use right ascension and declination. That's what it assumes by default, but you can also give it galactic coordinates or ecliptic coordinates if that's your bag. And you know, you can put in a name, and you can tell it use NED or Simbad to resolve the name into coordinates. Then you have to tell it the size of region that you want. And then the next big choice is what survey you want to use. We're going to talk about the list of surveys in a second. I would recommend that you turn off catalogs until you're ready to deal with them, because the catalogs can be overwhelming. So the different choices of bands, there's 2 optical surveys, and then the rest are infrared surveys. So the 2 optical surveys are DSS, which is the Palomar Observatory Sky Survey, specifically the digitized photographic plates. And so there's basically 3 bands, blue and red and near infrared. And there's multiple epochs of some of them. So there's scanned photographic plates from DSS. And then the Sloan Digital Sky Survey has covered huge chunks of sky in the Northern Hemisphere. And they have 5 bands, blue to near infrared. And then all the rest of them are infrared. So 2MASS is the 2 micron all sky survey, and it observes, it has data from the near infrared, which is JH and K, basically 1 to 2 microns. We've got WISE data, the Wide Field Infrared Survey Explorer, that's between 3.5 and 22 microns. Then there's the SCIP, which is Spitzer Enhanced Imaging Products, which is 3.5 to 24 microns. There's Akari, which was a Japanese satellite. It had short wavelengths and long wavelengths, but they have only, the Japanese Space Agency has only released the long wavelength images to the public. So we have data in there from between 60 and 160 microns. And then the IRAS, which is the one that I mentioned a little while ago from the 80s with the gigantic pixels, that's between 12 and 100 microns. So it turns out you can also load in a FITS file from other URSA holdings or off your disk or off other places on the web. So you put in what you want. For this example, I've got M16 and I'm picking almost all the bands except for IRAS. Then you click search and it gives you back the images. Now they come up by default in reverse grayscale, you see. And you can see that I've requested a relatively tiny chunk of sky because there are the talons from the Eagle Nebula. So there's 4 of the DSS plates. You can see that some of them were taken in the 1950s and some of them were taken in the 1980s. And then there's the 2MASS images and then WISE images. And if we scroll down further, oh, sorry, it summarizes your search up at the top. And then it's giving you 1 survey per row. And these are the real FITS files that you're interacting with. So you can use this toolbar at the top to interact with these FITS images. So you can you can get help interactively throughout all of this. If you want to change the color table or the color stretch, those pull downs will help you do that. And you can make the images big. You can make them take up your whole browser screen if you want. There's also a really helpful button right here. That's a 3-color button. If you hit that button, it will automatically create for you a 3-color image at the end of each row using 3 of the bands that it's returned. And you can see that the Spitzer data there has picked 3 of the IRAC bands. And then you can see Akari has larger pixels, it's longer wavelengths. And then there's the IRAS images with the ginormous pixels. So Akari and IRAS both have low spatial resolution compared to the others. Okay, so and if you want to download them to disk, you click on download, and then you can save them to your disk and play with them offline. When you go to download them, it comes up by default, downloading them as FITS, right? If you really want, if you've changed the color table and stretch exactly the way that you want, you can save it as a PDF or PNG or even HTML. But if you want to continue to work with the FITS images using Adobe Photoshop or something else, obviously you need to save the FITS images. And then the rest of it has to do with exactly how it's bundling up the files, for example. So some of the things you could do is, I'm sure you have a favorite object. So go and investigate what's bright and what's faint in each of the wavelengths. Is it the same thing that are bright in each one? Hint, probably not. You can pick a Messier object of each of the broad types, like a nebula, globular cluster, galaxy, and go and see what it looks like across these wavelengths. You are going to have to get different sizes of images because, for example, M31 is going to be way bigger than a globular cluster, for example. And so the Messier objects are going to look really different across these wavelengths. In general, some of them are going to look the same. And so there's a lot of astrophysics in what's bright and what's faint in these various bands. I'm sure that you can find images of something that you've taken an image of with your own setup. You can make a 3-color image with your image as one of the color planes. But in order for that to work, the astrometry in your FITS header of your image has got to be good. So if you don't have astrometry in your FITS header, you can try astrometry, not astronomy, but astrometry.net if you need to fix your header. So URSA's YouTube feed has several different movies on Finder Chart, as well as the other tools at URSA. And I'll give you a demo in a second. Yeah, let's do that now. Let's see if we can do this real quick. See if I can get, great. All right. So, of course, it doesn't put it in the right place. Okay, so this is the main URSA homepage. And it's got several tools here. You can, if you want, just type in your source right there and see what URSA's got for your target. Well, let's go with Finder chart. That's the one I was talking about. So if you click on the Finder chart link, then you get dropped in here. So we were using M16 before. Let's use M101. 300 arc seconds should be fine. I'm going to not ask for Akari, but I'll ask for all the others, and I'm going to turn the catalog off. So search, and there's M101, and it's going to load in all of these images. It's going to zoom in and out as it's trying to adjust them all so that they're all in the same orientation with north up. So all of these are the same patch of sky. And if you want to change the color table to something else, you can. If you want to change the color stretch to something else, you can. Depending on what you want to highlight in the images, you may want to pick a wildly different color stretch. What's the other big thing I wanted to show you? Oh, you can measure distances on here, right? So you can see how big the galaxy is. Let me put the grayscale back because it's easier to see. So this is 243 arc seconds, roughly, from that side to this side of the galaxy. You can put in coordinate systems if you want. You can put in compass rose, lots of things that you can do here. Let me go back and turn on the catalogs so that you can see why I'm suggesting you don't do this till you're ready for it. So I'm going to turn on catalog search within the image boundary. So it's going to load the images, and then the catalogs will go on top of it. So the DSS doesn't have a catalog that goes with it, but Sloan does. It's going very slowly. There's the 2MASS catalog, there's the LAAS catalog, there's the Spitzer catalog. All of those are sources. Let me make that into something that's easier to see. Instead of pink, let's make it purple. So yeah, lots of sources, so many sources that it's sometimes difficult to see the image underneath, which is why I recommend turning off the catalog search until you're ready. But when you are ready for it, there's lots of cool things you can do. You can see it's giving you the catalog here on the left, and it's giving you a plot on the right. Now it's giving you just a plot in RA and DEC, which doesn't seem very interesting, but you can change what's plotted. So for example, you can do a color magnitude diagram if you know what that is. W1M Pro is Y's 1 magnitudes from profile fitting minus W4M Pro. And then for that y-axis, we're going to do W1M Pro. And we're going to reverse this so the bright objects are at the top. So there is a color magnitude diagram from Y's of the data in all of those star forming regions that Y's is picking up in M101. So there's lots of cool things you can do. Lots and lots of cool things you can do. So let me go back to the last few slides that I have here. Come on. Oh, don't give me. Okay, there we go. Okay, so if you are more interested in the planets, there is a huge, incredibly vibrant community of so-called amateurs who play with the NASA images of planets. The stuff that came back from Cassini, but also currently coming back from Juno and Mars. The images are often posted to these archives just as soon as the DSN gets them back. So often you're looking at them at the very first time, just like the scientists are. And it's brand new data, hot off the presses, and you might even be getting to it before the scientists can get to it. So Emily Lakdawala at the Planetary Society is a huge supporter of this community, and she has a huge number of tutorials on how to access and play with those images. So lots and lots of cool stuff that you can do if you're more interested in the planets. So to sum up, there's a lot of data already out there, and a lot is available just via the web. You can do citizen science and you can do real science. You can also poke around in the archives and get real data, but you do need to know some basics. You need to work with FITS files, not PNGs, JPEGs, or GIFs. You can change the color and scaling to whatever you want to bring out whatever details of what you want, because you're not changing the data, you're just changing how it's being displayed. To first order, if you see something strange in the images, it's probably an artifact, not aliens. And you can poke around in the web interface as much as you want, because you can't break anything, and you can learn some really interesting things. There are tons of archives out there, and there's a very rich community of people working specifically from images from other planets in our solar system. So at this point, it's entirely possible that I've kind of blown your mind a little. So I've got all the links as well as a copy of the talk available there. You can either use a QR reader on your phone, you can copy that link there. And if you know a high school educator who wants to get involved in real research, talk to me, send me an email. I can tell you about NITARP. So if there's any questions, I'll be happy to take them. Do not see any questions in the chat.
Remember, everybody, you have to unmute to ask her a question.
That means either it was incredibly easy to understand or it snowed everybody.
Yeah, I don't know
have a
which it is.
question, actually. For the database you just showed us that you worked on, what exactly are the opportunities that people would get in searching through that database and working with those images? Because you showed us like how to use, but like what kind of things would they ask you to do with those images?
So the stuff that citizen science is much more focused, and the stuff that they'll ask you to do within the context of citizen science is spelled out very specifically on their website. The stuff that I just showed you is the professional interface. It's so you got to come up with the idea.
Oh, okay.
I gave you some ideas there of things to just explore with, you know, what images, you know, what is bright and what is faint in the optical and the infrared. And there's lots of good stuff that's in there. But if you want to get into actual research projects, that's a little harder because the interface that I've shown you is the professional interface.
Okay.
It's the real thing.
Okay, that makes more sense now. All right, I just want a clarification there. Thank you.
Oh, there's a question. Yeah, there's a question in the chat box. What specific science do you do with images you download? Do you mean me personally, or did you mean the same question that was just asked? What could be done? Don't hear an answer from that person. So maybe it was the question I just answered. There was somebody else who was trying to ask a question.
Yeah, so sometimes you see people say they process an image using a Hubble palette. What does that mean?
It means that they've picked the same colors as the Hubble people do and the same stretch, because the people that are doing the public release images are trying to make an image that highlights whatever the science result is. And sometimes it's just a pretty picture, but sometimes it's a specific thing that they're trying to highlight in the image. But they may be choosing a particular color palette or a particular color table that maps to the bands that they're using for Hubble. I think that's what you're asking.
Okay, yeah, okay, thanks.
Somebody else in the chat window asked, what do I do with the infrared images? So I study star formation, but I also study how stars vary as a function of time. So the sun has sunspots that even at its most active, the sunspots only cover a couple % of the surface. But if you go to a star that is much younger than the sun, same mass, but much younger, it has enormous spots that are maybe covering most of the surface. And so when those spots rotate into and out of view, you can see changes in the light that you get from the star. And the people that look for planets want stars that don't have a lot of star spots. They want quiet stars so that whatever dips they find correspond to planets. I care more about the stars. So I study I'm using the same data in many cases that the planet hunters are using, but I care about how the stars are varying. And so based on that variation, I can figure out how fast the star is rotating. And then I can try to understand how the star's rotation changes as a function of time, which is important for forming planets and understanding how and when planets form. Is you have to understand the angular momentum, the spin, the rotation of the system matters. Because, for example, Jupiter has most of the angular momentum in our solar system. So understanding the rotation rate of the star has ramifications for planet formation. So that's what I do. Can you give some example of specific science one you could do with downloaded images? So the examples that I had here, come on. So I'm sure you have a favorite object. You can go and get the images of that object and see what's bright and faint in each wavelength. You can get a Messier object of each type, right? Or an NGC object, whatever you want. Pick a bunch of galaxies, right? Because you can pick galaxies of a variety of types. You can have some spirals, some ellipticals, some edge on, and see what it looks like across these different wavelengths. And it is going to look different across the optical to the infrared. I'm sure that you have data that you've taken with your own telescope, so you can use your data as one of the planes in the image. So there's lots of things that you can do just playing with the images before you even get into the catalogs. If you know what a color magnitude diagram is, you can do those just like I showed you very quickly, and then you can actually look at you can look, for example, for things that are bright in the infrared. When I'm studying star formation, I do those kinds of color magnitude diagrams, and the things that are bright and red tend to be the young stars. So there's lots of things that you can do, but I can't give you like a nicely packaged worksheet to work through, not yet. I'm hoping to have some maybe in the next year or so that will actually take you through doing like basic simple science on the archives, but I don't have anything right now that does that. Are there more questions?
If I, as a citizen scientist, discover something interesting in this data, who do I report it to, and will they listen?
The people that are running the citizen science are the people that you would report it to.
Good.
And yes, in general, they will listen. And, you know, the evidence is really the list of authors here, right? Because the majority of the authors on these papers are citizen scientists in many cases. So there's usually within these citizen science programs, there's a way to sort of flag objects as particularly interesting. And that's how these things are, you know, are discovered, right? And, you know, you might even have an object named after you. So the original citizen science project, the Galaxy Zoo, there was a young woman from the Netherlands who, I think, Netherlands, who started playing Galaxy Zoo only because she was a fan of, what's his face? The band who does We Are the Champions, Queen. She's a fan of Brian May in Queen. And Brian May is a PhD in astrophysics. And so because of that, she got started in a Galaxy Zoo. Her name was Hanny. She found something interesting, and in Dutch, what is that, or some unusual thing, is voorwerp. So there's Hanny's voorwerp is an actual thing. You can Google it, and it's named after the citizen scientist who found it. So yeah, you can, but you have to work within their framework, right? You have to report it within their framework. Let's see, there was more questions here. What do you look for? What do you look for in star formation? Have you a quick example of what you've looked at? Is this work you do comparative from one image in the past to another image in the present? So the stuff that I was talking about with stellar rotation, our sun goes around in orbits, it rotates once rather, in about a month-ish. The stars that I studied, the much younger ones, sometimes go around in hours rather than days. So I'm looking at data that are taken, observations that are taken every 30 minutes for a month or two. And then I'm looking at the brightness changes over a month or two. And then some of the other stuff I do is looking at how those stars are changing now compared to how they were changing 5 years ago. And are they doing the same thing? Because if I'm looking at a rotation rate, it better be the same. Does that make sense? And then so stars form on timescales that are very, very long compared to human timescales, because a million-year-old star is a very young star, but it's very long compared to a human lifespan. So the best way that I can study star formation is by studying stars forming in many different regions, and then build up a story of how stars form based on those observations of many different regions. Can one help out with ongoing research? Yes, through these citizen science programs. Just go pick one and dive in. If they're actively soliciting participants, then they're actively doing research. With spectroscopic data, you could get redshifts and rotation of galaxies, absolutely. But I didn't show you any really cool spectroscopic tools because URSA has, at this moment, more images than spectra, but not for long. We are going to be getting a lot of spectra in the very near future. And so there's a lot of work right now behind the scenes on getting really good tools to work with the spectra as well. Okay, more questions? It's really weird to not be in the same room as you guys.
But a lot more comfortable.
Yes, and much less driving time, I have to say.
Well, that was quite enjoyable. It seems to me that you kind of really need to already know what you want to look at or find and how to ask for it before this will really work. Because the massive data is there is fantastic, but without a real question in your mind and it's pretty specific about what you want to know.
Yeah, so that's true, but you can start simply, right, with just the images. And there's a lot of astrophysics to be had just in looking at the different images, because you can, once you've mined all of URSA's resources, you can start to include the images of the same object in gamma rays or in radio. And then you can start to see really different things across the same galaxy. You can see many different things in the galaxy. It's all the different wavelengths are highlighting different physics that's going on.
I see.
So there's lots to be had even with just the images. But yes, if you're going to get into the catalogs, it does help to have a specific goal in mind, which is why I was ultimately trying to come up with some kind of like labs that you can do. I don't have anything really good right now, unfortunately, but I'm working on it. Can you recommend a citizen astronomer project that doesn't make your Mac explode with the huge images? Yeah, because most of the citizen science projects at Zooniverse are all web-based. So you're not downloading any of the images. You're just interacting with the image on the page. Like this one, this is Disk Detective, which I think they've now launched Disk Detective 2, which is the next phase. And the same people are also doing something called Backyard Worlds. They're looking for brown dwarfs and Planet X, basically in the outer reaches of our solar system. So in this case, you're looking at images, right? And the tutorial that I've got a screen snapshot of here is training you for what you're looking at in the images. But there's also one called Planet Hunters, which is looking for planet dips. So the light curve that they have in the background, that's brightness as a function of time. And all of these the points up here are the star variability, but these dips are the planet moving in front of the star. And so this tutorial is trying to show you, okay, this is what we're looking for. We're looking for these tiny dips that happen at regular intervals. That gives it away that it's a planet. So none of these involve downloading data. You're just interacting with the image on the page. And so you could even, I think, do it from your phone. I don't think you need a ton of disk space or bandwidth to do it because it's all packaged up for you in their interface. Okay, any other questions?
I just wanted to remind everyone that this meeting is also being recorded on YouTube. And so if anybody wants to go back and replay any parts of your presentation, they can do that on YouTube.
You can rewind me. You can slow me down. You can speed me up. It's really useful.
Looking at a recent HP Ren camera at Mount Wilson, it looks better than the last one.
Oh, that's really, really good news.
Let me see, I can, I'm gonna override your screen share.
Yeah, I did, I quit.
So you don't see the flames anymore, which we did before. So they've at least knocked it down to below the ridge there.
Excellent.
I don't know how long the exposure is on those images, but it's probably relatively long. So it might make it look worse than it really is. As you look south, you can see the fires actually burning up to Mount Harvard around the observatory. And they're probably just letting that. Who cares about Mount Harvard anyway? I think that may be where KPCC's transmitter is.
Yeah, I think so.
That's the edge of it on the, looks like the north side.
Oh dear.
Yeah. That's east, that's where it's coming. All right, just an update. It looks better than it did before.
Yeah.
I probably still won't go to sleep early tonight anyway.
I agree.
Yeah.
All right. Well, if there's no more questions, I'm gonna mute. And if you guys have questions you think of later, feel free to shoot me an email.
All right, thank you very much.
Thank you.
Yeah,
This was
thank
great.
you very much.
No problem, my pleasure.
That was a very good presentation, Dr. Luisa. We really appreciate that.
Mercy buckets.
And hopefully everybody can play around with it and figure things out, especially it sounds like Elizabeth Wong wanted to do some playing around with it to see what happens. So, okay, Spencer, is there anything else on the agenda we need to cover on tonight's meeting?
No, that was it. I think we got everything.
Okay, I think we could probably adjourn the meeting if nobody has any other comments. Anybody else have any other comments before I adjourn the meeting?
Well, I have one question for John and Kevin. Are we doing anything at Lockwood this coming weekend?
Why don't I put up the email blast and just so people can sign up if they want to go up. You know, it's only up to there being a star member there, and I can get an idea to see if there are any star members going or not. Otherwise, I would probably say no. I don't think it's going to be happening.
Actually, my question is more in terms of, are we doing another work party up there?
Oh, pardon. Another work party. Yes, there's going to be something I need to talk to John.
Okay.
Hello.
Where's John?
So Al sent me pictures. Al finished cutting all of the decking for the part of the ramp that we had built. So that I'll forward that to the board. But he ran out of deck screws, so he only put one screw in each plank on some of them, on each side. So on the ramp, what we need to build next is the handrails. And so that's probably a day project. And then if we have enough people, I want to work on getting the trailer leveled, the Explore Scientific semi-trailer leveled and stabilized. We've got all the equipment up there. We just need to have a little time to get it done. Also got lumber to build the back steps for the emergency exit from the trailer, but since nobody's using the trailer, that's not really a high priority. But so that's what. But the lumber, the supplies are up there. So those are the things that we can work on. You also mentioned at the last committee meeting, we need to repaint the white borders and numbers on the pads. And so that's something people can work on. That's a good idea to get that done before the cold weather sets in. I don't think, well, I won't be staying to do any observing. Because my wife's quarantined for COVID, I come home at night. I can't stay up there overnight. But the weather predictions don't look that good, so I don't know if anybody will be staying over for imaging or observing.
So Kevin, you're gonna send out a sign up sheet just for anyone that might want to go.
Yeah. So let's see if we have some people wanting to go up. I can state in the message that it's possible work party. Let's see how many people we can hook. Okay. All right. Does that sound doable? And we'll just say for this Saturday.
Sure.
John.
Yeah.
Okay. All right. I'll go ahead and send that.
I'm planning on coming up between 9 and 10 to get the gate open.
Okay.
On Saturday.
Right.
Excellent.
All right. Okay. Thanks.
Thank you.
Okay, the other issue is Ford Observatory is closed. The forestry, the U.S. Forest Service has closed the forest area, and Ford is closed. But last couple of weekends up in Wrightwood, it's been very, very smoky. So no, we're not going to open Ford anytime soon. At least until we get the smoke cleared and the fire's pretty much out. Because remember, a couple of years ago, we had that mirror re-illuminized, and we don't want to get smoke and dust on it. I'm gonna minimize the dust on it. So Ford's closed, basically. Okay, does anybody else want to discuss anything at the meeting here?
Yeah, this is Dan. I just wanted to give a second, to agree with Luisa that Galaxy Zoo is very easy to use. Kaz has been using it since he was like 6 years old, so it's super easy to use. Anybody can use it, and it's very helpful to the scientists.
Okay, well, thank you for your comment. Any other comments, questions?
Yeah, old Jack here out in Colorado. That was an excellent meeting and thoroughly enjoyed it. Is Mike Gardner still on?
Yeah,
Mike.
got his mic off.
Mike Gardner? Oh, okay. One growl I had is it seemed like Zoom dumped me about halfway through the presentation.
I'm back.
And I had to do some scrambling to get reconnected, but I managed to do so. Mike, you're there.
I am.
You remember about 68 years ago or so, your uncle built me an equatorial mount?
I remember.
Well, it's sitting out in my backyard. Yeah, it's sitting out in my backyard right now with a 3.5-inch Alvin Clark on it, and thumbs up the whole way.
Oh, good. By the way, I want that mounting back now.
With or without the telescope?
Well, leave the telescope.
Wow.
I'm glad it's being of good use to you, Jack. That's great.
Yeah, I played with that thing last night, and I did the intra-extrafocal diffraction star test. That lens is perfect, period.
Wow, that is wonderful. That is. When did you get that?
Those old toads knew what they were doing. I got it at the end of last year.
Oh, okay. Wow. So
Our webmaster said that he had a guy online here that had an old telescope, wanted to know more about it. So he emailed me, and we sort of got connected. And the guy got this thing at a flea market.
Oh,
and it was on his mantle as an object of art. And I didn't load it. And he did his homework. So I didn't pay yard sale price for it by any means. But
yeah.
But I got the darn thing. Absolutely mint condition. All the eyepieces, everything else went with it, but no mount or tripod. So your uncle has bailed me out.
That's very good. What type of eyepiece were they building?
Huygens.
They were Huygens. Okay. Yeah.
And Huygens eyepieces are not bad. They're actually quite good if you don't push them. You know, F15, they're great. F12, well, pretty good. F8, they're terrible.
Yeah, yeah. So how many did you get? How many eyepieces were there?
4 original, and one looked like an aftermarket Ramsden with a 100th-inch scale and a crosshair in it.
Oh.
Got some other barrels with some negative lenses and looked like Barlow lenses of some sort.
Yeah.
And I'm still trying to figure out what those are all about.
Yeah. So you're having fun with it?
Oh yeah, you betcha. And it's a lot easier to wrestle with than the 6-inch, I tell you.
Oh gosh, yes. Must be 4 times, 5 times lighter.
It's probably it's about 14 pounds, and the tube assembly on the 6-inch is 40 pounds. It's a lot heavier
14,
than it looks. I don't know.
Hey Jack, Curtis here.
Yes.
Hey, haven't seen you since RTMC, whenever the last one was, and the last one you made it out there. So
well, I made the last one. The last one, you toads had it moved to the conflict with the Okie-Tex.
Oh, okay. Well,
What do you mean, toads? Don't blame us.
Yeah, don't blame us for that. No. What some of us have been doing in the last 3 or 4 years, we've been going out to nightfall. They canceled that for this year, but I think the hotel's still going to have a dark sky weekend or something going on. I'm not sure exactly what the deal is, but yeah, a lot of us has been going to nightfall.
Sounds good.
Yeah, so at least one of these times we got to get together again.
You betcha, absolutely.
I remember that. I remember that time many years ago where I had my 6F15 Jaggers, and you and I spent half an hour walking back and forth with an eyepiece in hand to try to figure out who was better.
Yeah, you gotcha. As I recall, it was a draw.
Yeah, I think so. We just shook hands and we said the heck with it.
Pretty good Jaegers then.
Yes, it was a very good.
Jaegers are excellent lenses. They one of the guys out here did some interferometric tests with SR Clave, and Clave's eyepieces I still think are the finest on the planet. Their objective lenses seem to have a lot of secondary color, and I can't remember his name off the top of my head, but he had the Star Tracker company. And he went up to Ball and did interferometric tests on Jaegers versus Clave. And Jaegers beat the living seeds out of the Claves.
Whoa. Wow.
Yeah. Well, Jack, currently I have my old 4 1/4 f/15, got a 4 f/8, and I've also got a 6 f/8 Jaegers refractor, and that's a really nice telescope.
Those are good scopes, you betcha.
Oh yes, I remember the good old times.
Yeah. Well, I am going to highly recommend, beyond belief, the Okie-Tex Star Party.
Oh yeah, if you can send us send one of us a flyer on it so we can possibly put it on our announcement website or something, maybe we can get a little more popular in Okie-Tex.
Yeah, well, I should be there right now. It's halfway through their 8-day star party, but COVID seems to have given it the deep six. But
definitely keep us updated on it as far as next year's. Okay.
You betcha.
Okay.
Well, Google Okie-Tex Star Party.
Okay. Okay.
That'll do it. Right.
Google Okie-Tex.
So do you have any other discussions, or should we go ahead and, because I know it's getting to be 11:30 over there in Colorado with Jack Eastman. He's probably getting tired.
I'm stopping the YouTube recording.
Go that?
I'm stopping YouTube recording, but you guys can hang around and chat.
Go ahead. I think I'll go ahead and officially pound the meeting adjourned for tonight. If there's nobody has any other questions, official questions, I'll go ahead and adjourn the meeting for tonight.
Hey, Curtis,
everyone.
Hey, Curtis, this is Greg, and I kept my usual notes for tonight. I'll file those away if you ever care. And I've got us adjourning at 9:28.
Okay, sounds good. Okay,
Yep.
The meeting is officially adjourned. I'm going to go offline then. Okay, guys? You guys take care.
Bye.
Okay, bye.
All right, bye.